In today's topic video, we're going to be talking about the rational roots theorem. What this theorem does is, given any arbitrary polynomial, it allows you to generate a list which contains the zeros to your polynomial. So let's take a look at what we're talking about. So say I've got a polynomial, call it p of x, that looks something like this. Q x to the n plus c1 x to the n minus 1 plus c2 x to the n minus 2, and so on, all the way up to p x to the 0. Now, this is just the generic form of a polynomial. So this could be like 7x cubed plus 2x plus 3 or something like that. Keep in mind that x to the 0 is really just 1. So at the end here, we've really just got a plus p going on. I wrote x to the 0 to be consistent with the format here. Now the reason that I've just got c1, c2, in other words, a bunch of constants in the middle, is because I don't really care about those for this theorem, but I very much care about p and q, the front coefficient and the constant at the back. Those are the things I care about. Now what the rational roots theorem tells us is that if I take all the factors of p and divide them by all the factors of q, one by one, and I do both the positive and the negative values for that, I'm going to get a list of numbers. In that list of numbers, my rational roots are in there. In other words, the rational numbers that make this equal 0 will be in that list. That's all this theorem tells us. So, for example, if my p happened to be 8 and my q happened to be 20, and I wanted to make my list, then what I would do is I'd list out all the factors of p. So for 8, that's going to be 1, 2, 4, and 8. So notice it's not the same as a factor tree. I'm not splitting it into how many 2's I have. It's just literally all the numbers that divide into that. So 1 goes in, 2 goes in, 4 goes in, and 8 goes in. And then for 20, I'm going to have 1, 2, 4, 10, 5, and 20. Let's make sure I didn't miss anything. 1 goes in, 2 gives me 10, 4 gives me 5, 10, 2, 5, 20. So there's all my factors of 20. My list, my rational roots theorem, tells me that my following list is this. Now I'm going to put a plus and a minus on the outside. This is just the way I'm writing it. What I'm saying is for every number I list here, you're going to have both a positive and a negative one. So first I do p over each one of these different things. So the first factor of p is 1. So I do 1 over every single one of the different q's. So 1 over 1 is 1. 1 over 2 is 1 over 2. 1 over 4. 1 over 10. 1 over 5. And 1 over 20. And you may already be like, oh my gosh, this list is long because I've done the 1 overs. Now I do the 2 overs. Now, there's a couple things here that make this not as bad. First of all, 2 over 1, I don't have that, so I put it. But if I do 2 over 2, that comes out to be 1, and I've already listed it. So you do not need to list repeats. So I skip that. 2 over 4, I've also already got that. 2 over 4 is 1/2, so I don't need that either. Okay, 2 over 10, well, 2 over 10 reduces to 1/5. I've already got that as well, so I'm not going to list it. 2 over 5, okay, now that I don't have, so I'll put it 2 over 5. 2 over 20, well, that reduces to 1/10. I've already got it, so I don't need it. And now I do 4. 4 over 2 is 2. I've already got that. 4 over 4 is 1. I've already got that. 4 over 10 is 2/5. Already there. 4 over 5, I don't have him, so I'll go ahead and list him. 4 over 20, that's 1/5. I've already got it. And let's just finish off with 8. So 8. Already got 4. Already got 2. 8 over 10 would be 4/5. Already got it. 8 over 5, I don't have that, so we'll list it. And then 8 over 20, that's going to be 4 over 10, which is 2/5, and I've already got it. So there's my whole list. Now, that looks really long and my numbers aren't even all that big, so this might look pretty scary, but here's the important thing. Granted, you could be pretty unlucky, I suppose, but you don't have to do every single one of these. What you would do is you could use your hunch a bit if you look at your formula and you think one of these works, but just go through them. So try one, plug that in, see if you get 0. If not, move on to the next one, see if you get 0. If not, move on. As soon as you find one that works, that is a 0 to your polynomial, you would go ahead, do synthetic division, then your polynomial is going to get smaller, and you can remake your list with your new polynomial, and you'll have a shorter list and fewer numbers. So just because you get a long list like this, it doesn't mean you actually need to do every single one of the numbers in this list. It just means you need to find one of the zeros in here. So what the rational roots theorem tells you is that for rational roots, they're in this list. Now, of course, you could have square roots, which are irrational, like square root of 5, square root of 2. You could also have imaginary numbers, right, like 3i or negative 3i. Those won't be in this list. So don't despair if you're going through the list and none of them seem to work. Instead, you take a closer look at your polynomial and go, ooh, maybe this doesn't have rational or real roots. So that's the rational roots theorem in a nutshell. All it's saying is if you've got some polynomial and you're trying to find the zeros of it, a way to know where to start is to do all the factors of this last number over all the factors of the front coefficient, and then this list has those zeros, if they're in there. All right, now that you've seen a general overview of what the rational roots theorem is, here are some examples which actually make use of it. In this first example, we use it to factor a polynomial which has exclusively rational roots. In this second example, the polynomial which we factor contains some irrational roots. Both of these utilize the rational roots theorem.